All right, so picking up where we left off last time, we talked about pseudocode, how it's fake code, and there are no rules for it. They're just guidelines. And then we gave an example here for linear search. And now what we want to do is we want to analyze this actual algorithm, right? That is, as the input size grows, let's quantify how good or how bad this algorithm is. And when you go to do algorithm analysis, there's generally a 5-step process. The first 3 steps are just setup, right? So you need to identify the input, you need to identify the input size, and you need to identify the elementary operation. The input and the input size, if you've written good pseudocode, that's probably pretty straightforward. However, there are instances in which you have to make decisions. So we will go over the details of those in a second here. But otherwise, identifying the elementary operation, that goes back to when we started up here with these engineering considerations, right? We're not going to, we have to identify something in order to quantify that something. But we're not going to identify particular GPU instructions or how many bytes it takes or something like that. We're going to try to keep it general and generic. In other words, we're going to identify, and there could be more than one solution here, by the way. If I choose, I want to analyze this with respect to additions, or I want to analyze this with respect to comparisons, right? Those might lead to 2 different outcomes, 2 different analyses. Neither one of them is right. Neither one of them is wrong. It just gives you, with that setup, here's the outcome, right? The actual work is done here in step 4, where you determine how many times the elementary operation is executed with respect to the input size. In other words, you're going to come up with a function. You're going to come up with a function f that says on an input size of n, it has a behavior of n and it's linear, or it's n squared, or it's exponential or something. And then we're going to quantify that using big O analysis. Okay. So again, we're going to have to look at a couple of the first 2 should be straightforward, but a lot of the times there are caveats, right? So let's talk about identifying the input. Right? Again, generally this is given as part of this pseudocode, or if you've written good pseudocode, you've already identified the input. However, in some cases, it is unclear, or it is less clear. Less clear. There we go. For example, what if you have multiple inputs? Right? For example, over here in linear search, right? I have multiple inputs here. I have, let's highlight this. Right? I have A, which is the collection here, and I've also got the key, E sub k here. Right? Now, be careful when you're considering these inputs. There are n inputs over here, but we don't consider all of those. Those are all part of the same collection here. So I'm given one input over here and another input over here. If you were talking about this as a method or a function, that function would have multiple inputs. Right? In C, it would be int star array, right? That's the array. And then you'd also have int n, which is the size of the array. Right? Which one of those is more important, though, with respect to this algorithm? Right? Which one of these, either the collection or the key, is going to have an actual effect on the performance of this algorithm? Right? Well, you're doing a for loop, right? And you're iterating over each one of these things in the collection. Right? That's going to change. If the collection only has 10 elements, then you're only going to be doing 10 things. If the collection has 10 million elements, you're going to be doing a lot more things, right? So this one, what about the key though? Right? Does that ever change? If this has 10 elements or 10 million elements, there's still only one element over here. The collection is going to have a much greater influence on the performance of this algorithm than this single key over here. So in this case, we would choose to focus on that one input there, right? Okay. So generally, you keep things simple. You only want to focus on one input. You choose the most relevant, or the input that has the biggest impact on the performance of the algorithm. Right? Okay. Let me fix that, okay? And again, our example here is linear search, right? The size of the collection will influences the for loop performance far greater than the single key. Right? So the input size in this case, we would say A. Right? Here's another example. Right? What about Euclid's GCD algorithm? What does GCD stand for, by the way? Greatest common divisor. And whether or not you've seen it before or not, that's fine. But just understand this, that it's basically a function, GCD of A, B. Okay? Here's a secret. GCD of A, B, it's not a secret. GCD of BA. In other words, does it matter what order you give the two integers in? No, right? But these are both numbers. So we have two numbers here. Numbers. Keep it simple. Choose one of them. Right? Now, what if I were to do the GCD of, say, 1024 and 52? Right? Okay. What is the GCD there? What is the largest integer that divides both of those things? 2 divides both of those things, but also 4 divides both of those things because 2 goes into them twice. So this would end up being 4, right? Now the actual algorithm, what you would do is you would say 1024 divided by 52 with a remainder of, I don't know however much remainder is. And then you would do 52 divided by that remainder, right? And then you'd have this remainder until you get down to a remainder of 1. And then that, whatever is left over, that's your greatest common divisor, right? I don't want to get into that though, right? What I want to do is I want to choose one. Choose A or choose B. In this case, which one of these numbers would have more influence on the performance of the algorithm? Just go with your intuition here. A bigger one, right? So it's as simple as that, right? Here there are 2 integers. The input is two integers, right? Without loss of generality, W log, right? Without loss of generality. Without loss of generality, right? Have you ever seen that before in mathematics? W log, without loss of generality. There we go. Focus on the larger of the 2, right? In other words, assume that A is greater than or equal to B, and then focus on A, right? And generally what you can do is, if that's not the case, if B happens to be greater than A, just switch them around. With the GCD algorithm, it doesn't matter. GCD of AB is equal to GCD of BA, right? All right, so without loss of generality, choose the larger one. Right? Always want to get it down to one input so that you are focusing only on one input. Second step, you identify the input size. Right? Again, this is simple, but it can be tricky. Right? There are some that are obvious, right? Collections, right? That is a list, an array, a set, a map, etc. Right? The size of the input is the number of elements in the collection. Now, in set theory, what do we call that? What if I were to write it like this, like that? Magnitude would be for numbers, and we'll come back to that. Remember that, right? I'm going to come back to you to ask you what magnitude is, right? But it's called cardinality, right? There we go, right? A little bit less obvious. What about a matrix? Right? It has n elements, or n rows, and m columns, right? Without loss of generality, what you can do is you can assume that n is greater than or equal to m, and so n c dot m, there we go, is less than or equal to n squared, right? So just go with n, right? In other words, focus on n, right? If it's the other way around, then just take the transpose of that matrix, and now they're swapped around, just like we did with the first with the GCD algorithm, right? Or another option would be, without loss of generality, set n to be mc dot n, right? And then n is your input size. And here I'm saying capital N, right? So just switch it up. Just change the parameter here and focus on that single value, right? What if the input is a single number? right? Say x, right? Or in this case, I'll just call it x, right? What is the size? What is the size of a single number? Okay. Now for that, let's look at an example here since we've got some extra time here. We're a little bit ahead of the main section. All right. What I want to do is I want to write another algorithm here, get more practice with some pseudocode. And my input is going to be an integer, x, such that x is greater than or equal to 2. Okay? My output is going to be prime if x is prime. And then what's the opposite of prime? Composite. Composite. And I don't say if it have to say that it's composite, otherwise. That's the other catch-all, right? Okay. Now, how would you go about doing this? Here's 4, 7, 8, 3. Right. Is that prime or composite? How would you go about deciding that? Well, does 2 go into it? Definitely not, because it's not an even number. Does 3 go into it? 4,500, 270, so we're left with 13. Nope, there would be a remainder of 1. Hopefully I did that right in my head. Would 4 go into it? Technically, I don't have to look at 4 anymore because I know that 2 doesn't go into it, so therefore 4 doesn't go into it. 5? Nope, because it doesn't end in 5. All right, so no, no, no. 6? No, I don't have to check that again because I've already checked 2 and 3, its divisors. 7? Does 7 go into it? No? Okay. 8? No, I don't have to check that. 9? All right, you get the idea. What do I have to go up to? Dot, dot, dot. What's the maximum that I would actually have to check? Square root of 4783. And I have no idea what the square root of 4783 is, right? Why did you say I only had to go up to the square root? Yeah, why is it, if this is n, why don't I have to go up to n by 2? That's even larger, by the way, right? Generally, right? I only have to go up to the square root because what is the, so these are small divisors. What is the maximum divisor? It would be when n is a squared. And so the square root of n is equal to a. Right? In other words, there are only 2 divisors, and it's the square root of itself. If you go any higher than that, guess what? It has a corresponding companion divisor smaller than that, right? That it would have been a times b, right? Where a is greater than this, well then b would have had to been on this side of the square root of n, right? Isn't mathematics awesome? Right? So here is my loop. For, and I won't concern myself here for just primes, for, let's say, d, running from 2 up to square root of x, right? If d, and here's some math for you, divides x, then I will output composite. Because I found a composite. Because I found a prime divisor here. Otherwise, if you get through all the possible divisors, then what do you output? And none of them divided it, then you output prime. Right? This here is divides with no remainder. In other words, let's go ahead and put in a comment here that this is x mod d is equal to 0. That's what that math means. All right? This is divides. If you've never seen that before, that's fine. All right? Well, from a naive perspective here, I would say how many times does this run? -1. Right? I would say that this for loop here runs how many times? About square root of x times. Right? All right, well, what if I were naive and I said that the size of x is x? Right? So the size of x is equal to x. So in other words, this runs for square root of x times. Right? Is this better or worse? Better or worse than linear? All right? Question mark. If I were to graph this, what would it look like? Here's linear, right? What does square root of x look like? Yeah, nope. Something like that, right? In other words, something, okay. It's not linear, but it is, there we go, something like that. It's lower than linear, right? It's better than linear. Right? Now, what I just described here is basically a variation of what's called the sieve of Eratosthenes. You guys know about Eratosthenes, 3,000 years ago, mathematician, right? So basically just try all the prime divisors until you find one that works, right? It's a brute force kind of way. It was only known in like 25 years ago of how to do this efficiently. This is called primality testing. Only 25 years ago did we come up with a polynomial time deterministic algorithm for this. Right? It's called the AKS algorithm. Right? For 3,000 years, this was how it was done. It was done by a brute force method, and it is definitely not. This is not linear. Right? It was not linear 3,000 years ago. And the reason for this is that we need to come back to our principles, our step 2 here, and we need to identify the actual input size. What is the size of a single number? Okay. So let me come over here and start to give you intuitions. 10 versus 10,000. Which one, just straight up, which one of those numbers is bigger? That's not a strict question. Definitely 10,000, right? So what's the size of those numbers? It's not 10, and it's not 10,000. If you said that the size of n here being 10 is 10, right? No. That means that you would be in a unary system like this, right? Where you're writing down hash ticks for it. You're writing down 10 symbols to represent 10. I'm going to go ahead and do the same thing for 10,000. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? I would sit here and nobody wants to sit through this, right? Where you're writing down 10,000 things. I didn't have to do that, did I? Because of this wonderful thing called number systems that was developed, what, 4,000 years ago? How old are Arabic numbers? Yeah, look that up for me, right? Some other systems would do something similar to this, so what we just did, ticks, right? Ticks. In other words, I. It's extremely inefficient. And in fact, some historians have contemplated that's what held the Romans back. Their inefficient number system. You can't do efficient accounting and stuff like that. Right? And so that's why they imported Arabic numbers eventually. 1, 2, 3, 4, 5. Algebra? Oh, what?
Algebra. Algorithms.
That's that's named for Al-Khwarizmi. I don't know who that is, but somebody.
That's the play that Romans had on them, and it was done when the Arabic eventually conquered Persia while simultaneously bringing Rome down.
Oh, okay. I don't know my history that well.
I love history.
All right. So eventually they adopted Arabic numbers. Right? Arabic numbers are much older. Whenever they adopted them, several thousand years ago. Right. So in other words, the size of a number is not the number itself. The size is the number of symbols required to represent that number. Right? In other words, base 10 numbers or base 2 numbers, right? Or base 16, right? That's the real size there. So how can I mathematically quantify that? Right? Mathematically, the size of a number, and you said it before, is the magnitude of the number. Mathematically, how do I determine what the magnitude of a number is? Good, right? So we remember our high school math here. You were introduced to logarithms in high school, probably without much explanation. Maybe they said that it was magnitude, right? But ultimately they just said, here are the logarithms. You need to understand them. You need to know these identities, et cetera, et cetera. Let me show you why it's important, okay? So suppose you have X digits, or no, I don't even want the number of digits. So suppose that I gave you 1 digit to work with, or 2 digits, or 3 digits to work with. What is the maximum number you can represent? Right. So this is base 10. We'll get to binary here in a second. But base 10, what is the maximum number that you can represent with just 1 digit? 9. If I gave you 2 digits, what's the maximum number you could represent? 99. And 999, right? Dot, dot, dot. What if I gave you k digits? 9999. There are going to be k of those things, right? Mathematically, what is that? 10 to the k minus 1. Why minus 1? Because you always start at 0, right? So, work backwards here. What if I asked you, here's a number n. What is the number of digits required to represent n? Right? All you have to do is set up that equality, 10 to the k minus 1, because that's what we derived over here. If I gave you k digits, you could represent this. I want to know what k is over here if I'm given n. That means solving for this equation right here. Right? K will be our answer. So n plus 1 onto the other side, 10 to the k. How do I get rid of that k? Log. Base 10, I'll be explicit about it here, plus n is equal to k. Right? Now let's repeat this. But let's not be humans here who have 10 fingers and 10 toes, and that's the only reason we use base 10. Right? Instead, what I'm going to ask is how many, not digits, but digits. And that was the original name of bits, by the way. Right? I always like doing that because it gives you some historic context there. It was actually called bidgets, and then, well, no, let's just shorten that up because it's a mouthful. Bits. All right? So now, if I gave you 1 bit, what is the maximum number that you can represent? 1. If I gave you 2 bits, the maximum number that you could represent is 1, 1. What is that in decimal, by the way? 3. Good. 1, 2, 3. 3 bits, all ones, is going to be 7. Right? Yeah, it's going to be 1, and then this is 2, and then this is 4. So add those all up, and you get 7. If I gave you k of them, dot, 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 k, what is that going to be? 2 to the k minus 1. It's exactly as before. It's just a different base system. Instead of 10, it's going to be 2. So now working backwards over here, n is equal to 2 to the k minus 1. Take 1 onto the other side, 2 to the k. And now how do I get rid of that k? Or isolate that k, I should say. It's going to be log, but in this case it's base 2 is equal to k. All right? All right, so let's just go ahead and shorten that up. It's going to be about log n, because I don't like that plus 1 there. All right? Just add 1 more or something like that. All right? So the answer here is the number of bits required to represent a number. By the way, it's not 32, it's not 64. Those are particular implementations. A 32-bit system, a 64-bit system is going to, in general here, is going to be log base 2 of n. All right, there we go. But as self-respecting computer scientists, or computer engineers or software engineers, want to be inclusive here. As self-respecting computer scientists, we just write that it's going to be log of n. Why? Because all of our bases are base 2. Right? It doesn't matter what base you put it in. It's the same to within a constant. Do we all remember the change of base formula? You were given logs in high school, and you were told, oh, you have to memorize all these formulas, right? You can always change the base by some constant, right? Do you remember the change of base formula? Log base b of a is equal to, let's go with x there, sorry. Log base a of x all over log base a of b, right? Well, what is log base b of a? Well, that's just some constant sitting out front. Let's call it c. And so now it's log base a of x, right? You can change from b to a or back and forth by simply just taking some constant out front, right? Unless the constant is what? Unless the base is 1. Now it all fails. Why? It blows up. It's now infinite, right? Okay. All right, so the input size is generally the number of bits required. Actually, let's go back now to my example here, right? We said that this was order, that it's square root of x. But that's not the input size. The input size is log of x, right? Let's isolate x because this is actually a correct answer, that it's going to do square root of x operations, right? It's going to do a square root of x divisions, right, and iterations. But that's not the input size. The input size is log x. Right? So what is x in this case? How do I get rid of the log? 2 to the n. So this is base 2, right? Again, all self-respecting computer scientists, we're not going to write base 2 explicitly. And so this is square root of 2 to the n. Right? Does that look better than linear? No. Ignore the square root for a second and tell me what that thing is right there. That's exponential, right? That's why 3,000 years ago, we only had an exponential algorithm for this. And only as of 25 years ago do we now have a polynomial time algorithm for this, right? So identifying the input size is actually important, right? It is a science, right? Okay. All right, 3, elementary operation. Ultimately, we want to focus on one operation to analyze. All right. We want a simple analysis. We don't want it to get too complex. So most of the time, you choose the most common or most expensive or most relevant operation, right? Generally, however, we do not consider any operation necessary for the control structure of the algorithm. All right? And what do I mean by that? Let's come back over here and let's translate this into actual C or Java code, right? So if I were to write a for loop here, for int I equals 0, I is less than or equal to n, well, let's go with less than n, right? I plus plus. We're actually doing something in here. Do something. Right? Now, there is a lot going on to actually do that something. For example, what I can do here is that this is, no, let's count this one right here. There's one assignment that is done at the start of the loop. There's one comparison for each iteration, right? There's an addition, again, for each iteration, right? And also, an addition is actually more than one thing here. It's actually an addition, and then you're reassigning the value here. So you're actually doing, a whole bunch of assignments, a whole bunch of additions, and a whole bunch of comparisons, right? None of those are relevant. Right? We're not going to count those because inside the loop here, you're actually doing something, right? Something more expensive or more common. Whatever you do, if you do like I divided by 2 or something like that, right? Then you're doing a division. But yes, you're doing an assignment, an addition, and a comparison, but you're doing the same number as whatever you're doing in here. Right? So focusing on whatever you're doing inside of a loop is going to be way more important. Okay? We're not going to focus on anything that is necessary for the control structure of the algorithm. Right? Some examples, as I've already said, comparisons. Right? For example, searching or sorting algorithms. Right? Arithmetic operations, for example, additions, subtractions, or mults, divisions. Why did I put those in two different groups? Are additions and subtractions, is one more expensive than the other? Think about what is a subtraction? It's an addition of a negative number, right? What is a division? It's the multiplication of a reciprocal, right? So subtractions, subtractions and additions, those are the same. Multiplications and divisions are the same. But what about, say, additions versus multiplications? Those are not the same, right? If you were just to do this in a grade school manner, what would it look like? 572, 572 times 134. They call this long multiplication. 4 times 2, that's 8, no carryover. 4 times 7, that's 28, carryover of 2, and so 22 right there. That's just one number. Now, 3, so move this over. Now it's 3 times that, that's 6, 21, and a carryover of 2, and 3 times 5, 17, right? Multiplication is what's called iterated addition, right? You'd end up doing 1 multiplication, 2 multiplications, 3 multiplications, and then at the end, you would add them all up, right? Or another way of looking at this would be 5 times 7, right? That's equal to 7 plus 7 plus 7 plus 7 plus 7, right? 5 times, right? So all you have to do a multiplication is just do a bunch of an iterated addition there, right? Okay. So it's way more expensive to do divisions and multiplications. What about linked list operations? What was our elementary operation then? What was the most relevant thing that we did with a linked list? I want to get the ith operation, or I want to get the ith element. I have to start at the beginning and I have to traverse. So node traversals. Right? This is similar for graph and tree operations. Eventually you will get into graph algorithms. I don't know if you do that in 235 anymore. You certainly would do that in computer science 3, right? Where you're doing depth first search, breadth first search, you're doing all this stuff on graphs. Well, walking around that graph, going from one node to the next node, that's your elementary operation, right? And then you process the data at each node, right? Okay. That's good. And we've got time. I don't think this is 5, this is 4. All right. Let's talk about analysis. That's where the real work occurs. Again, 1, 2, and 3, they're all just setups. Once you've done that, then you can start to work on the real issue here, right? Determining how many times the elementary operation is executed with respect to the input size, right? And I'll repeat that right here. In other words, you're going to come up with a resource function, right? So you have done this hopefully in 235, or if not, then you've done it some other time. I'm going to call my function t because it's time. If you want to, you can call it c, and that's going to be for comparisons. If you just want to call it generic function f, you can call it f. I'm going to call it t though. All right, and it's going to be a function mapping. What are those things right there? What is that that stylized n right there? That's the natural numbers, right? And it's going to map the natural numbers, right arrow, to this set, and I'll ask you what that stands for. There we go. What is the R? All real numbers, and then the plus above it means positives, right? So why did I write it like that, right? So let's indent here, right? Math BBN, this is LaTeX, by the way, right? There we go. This captures the input size, right? Input sizes are not negative. Right? That's why we go with the counting numbers or the natural numbers here. Have you ever heard of an array of negative 10 elements? Doesn't make any sense. Also, input sizes are not fractional, right? This is why this is why you're taking 235 right now. What is the title of 235? Discrete structures or discrete math. What does discrete mean? It means that it's not real numbers, right? It's integers. It's the natural numbers, right? Input sizes are not fractional. There's no such thing as a continuous, actually, here's a big secret of physics, by the way. Is the natural world continuous? No, it's not, right? Is energy infinitely divisible? No. What is the simplest unit of energy you can have? It's called a quanta or a quantum, right? That magically things jump from one quantum to the next quantum, and there's no in between, right? So is space infinitely divisible? No, it's not. It's so small that you might as well use continuous mathematics to model it, but no, you cannot infinitely divide space. Just like you can't infinitely divide time, you can't infinitely divide energy, right? All those things are the same thing anyway. But also from our perspective here, is there anything, does it make sense to talk about an array of size 10 and a half elements? No, right? All right. Why do I map it to the positive reals? Remember that that's called a codomain, not a range, right? And by the way, here's the LaTeX for it if you ever need to do something like that. Because we don't want to consider negative resources. What does it mean to run an algorithm to sum an array of integers and it took negative 10 seconds to execute? Is that a thing? No, that means that you start it now, and then 10 seconds ago in the past you had your answer, right? Now there are several science fiction things that you can do like that. There are quantum mechanics where you can travel back in time. You can send a particle back in time. There's a concept of that but that's just because the mathematics has to work that way. It's not actual time travel, right? There's no such thing as time travel, right? No such thing as time travel, right? In real life, right? Of course, science fiction, sure, go ahead, right? Also, we're only going to consider monotone increasing functions, right? We're not going to consider 1 over n or sine of n or something like that because those things oscillate, right? We want to consider monotone increasing functions. As the input size increases, the number of resources increases. That's what we mean by an algorithm, right? Actually analyzing this might require a little bit of art, maybe some summations or other calculations, finding closed form solutions, or even super advanced math. You won't be doing any super advanced math for this class, right? There is no clear guideline I can give you, right? Everything is going to be slightly different when you analyze something. Most of the stuff that you'll see is pretty straightforward, right? But otherwise, there are entire papers that take 30, 40 pages just to analyze one algorithm, right? And they use super advanced techniques just to get like the coefficient down to or the exponent down to by 1/100th of a value or something, right? Also, we're generally going to consider only the worst case scenario because we're going to keep it simple. We don't want to look at more advanced stuff like an average case analysis. We don't always want to be optimistic and think that it's going to be the best case, okay? All right. So let's do a very, very simple example to get us started, and then we're going to do more examples on Friday. Linear search. Let's go back to our linear search here. Give myself some more room. All right, so step one. Step one is to identify the input. And the input in this case is A, right? 2, what is the size of the input? Well, we also wrote good pseudocode here to tell you the size. How many things are in A? N. 3, what is the elementary operation? Or elementary operation for short. Yep. Oh, good. You immediately jump to this comparison right here. Should I pay any attention to line 1 right there? That's necessary for the control structure of the algorithm. Nothing there is relevant. We're doing something inside of that loop, and therefore we look inside that loop. What about line 3? Is that always executed? Nope. Line 2 is always executed though. So I'll say the comparison comp on line 2. Right? Step 4. How many times is the elementary operation on line 2 here, I'll highlight it, executed with respect to the input size? Now again, you can think of the best case scenario here. How many operations would you give if you got lucky? 1, because you find it at the very beginning, right? You could look at the average case, and it's going to be about n divided by 2. We won't go through that though. But what's the worst case? Yeah, yn. What is the worst case for this algorithm? Yeah, you go through the whole list, you find out that it didn't exist. Or you go through the whole list and it's the very last one. Right? You just got unlucky. Right? All right, so shuffle it and try again. Right? Don't do that. All right? So, a very simple answer here, n. Right? What kind of a function is that? Linear. Hey, I guess that's why we call it linear search. Right? It takes a linear amount of time. Fast forward here to step 5. This is going to be big O of n. It's going to be a linear function. We won't talk about that until we've done some more examples here. Right? Okay. Yeah, I'll leave it like that because I don't want to get into the next algorithm. Right? But there's your 4-step process, 5-step process eventually of analyzing linear search. That one's straightforward. What we'll do next time is we will look at another one. That's not my pictures. Files. iCloud. There we go. Algorithms. Why can't you just go to the last place I was always at? Come on. There we go. Remember this guy? Selection sort. How does it work? Goes through, finds the minimum element, and it puts it at the beginning by swapping those 2 elements. Goes through the remaining elements, finds the smallest element, puts that second. Goes through the remaining elements, finds the smallest element, puts that third. It's selecting the minimum each time. Right? And here's the pseudocode to do that. Again, step 1, 2, and 3, it's going to be straightforward. A is your input. N is your input size. What is your elementary operation here, though? Would it be any of this stuff right here? That's for the control structure of the algorithm. Would it be any of this stuff right here? That's for the control structure of the algorithm. Should I even bother looking at 2? I'm doing a loop within a loop. I probably want to pay attention to whatever's going on inside of that. Right? So I've got a comparison and I've got an assignment. A comparison is done every single time. An assignment is only done occasionally. So which one am I going to pay attention to? The comparison on line 4. Now here's the big question. How many times is line 4 executed with respect to everything else? Right? It's going to be n squared at the end, right? Order n squared at the end, but we need to formalize that. Right? And we'll go ahead and formalize that on Friday. Right? Any questions? Otherwise, remember that this Friday your design document is due. This is your this is your second to last draft. So make sure that you're doing a pretty good job at this point because you're only going to be able to get feedback 2 more times before it's actually graded.